In this video, we're going to introduce the concept of reaction mechanisms. And so up until this point, we've had a whole series of videos on looking at how we can determine a rate or a integrated rate law for a given reaction. What a reaction mechanism does is it expands upon those principles, and it actually starts to dissect a reaction and look at the various steps that are taking place within the reaction. So if you remember back to chapter 6, when we were looking at reactions, generally speaking, we're concerned about the products and the reactants, right? We're kind of concerned about the difference between the product and the reactants. And we do this oftentimes with things like enthalpy. We just compare where the products are versus the reactants to get a delta H. But in a reaction mechanism, what we actually are concerned about is not necessarily the products and the reactants, but the pathway that takes us from the products to the reactants. So when we talk about reaction mechanisms, we're talking about the steps that build up to give us an overall reaction. What we call the steps in a reaction mechanism are elementary reactions. And these elementary reactions are basically these stepwise processes that kind of all come together to give us the final overall reaction. And so the sum of these elementary reactions is what we call the mechanism. So, you have step 1, step 2, step 3, step 4, or however many steps. And when those combine together, that mechanism produces the overall reaction. So that's what we call the mechanism. And there's one important term that we have to introduce, and that is a reaction intermediate. So exactly like what it sounds is it's a intermediate. It's something that's produced, but it doesn't really hang around in the overall reaction. So an intermediate is a species that's produced in an elementary reaction, but does not appear in the overall reaction. So let's look at the following down below. This gives us some examples of what I'm talking about here. So we have our overall reaction, and this is what you guys are used to seeing. So this is what you guys would do the stoichiometry on. This overall reaction is what you would get if you were to look at like a delta H or something like that. And this gives us the overall stoichiometry, and this would be where we would start in order to understand the rate by writing a rate equation. So if we were to write a rate equation for this, we would say that a general rate equation for this would be equal to K times the concentration of A to the M and B to the N. Because we don't know what's going on with those A's and those B's. We don't know how they're reacting with each other. But what a mechanism will allow us to do, where we're kind of going with this, is that once we know the mechanism, we can start to actually come up with those M's and N's based on what's going on inside the mechanism. So let's look at this proposed mechanism. So these two steps down here, these are the elementary steps, and so this is our mechanism part. And what this basically says is we have a first step where we have the A's come together. So we have an A plus an A, and this gives us something called an E, whatever that is. And then in the second step, that E reacts with the B to give us our products, which are C and D. So now if we wanted to get the overall reaction from this, we can add these two steps up. We can add them or combine them. And if we do that, we get A plus A gives 2A. And then if you notice, the E cancels out because it's a product in the first step and a reactant in the second step. So that goes away. And then we have plus B, and this gives us C and D. So this is a plausible mechanism because when we add up the steps give us the overall reaction. So that means that it's plausible. Now this E is actually quite important. This E is what we call the intermediate in this particular case. So the fact that E is produced in the first step but then reacts away in the second step means that it's a transient species that's not observed once the reaction is complete. It's fully reacted away, and we don't actually detect it. We can detect its presence in very small concentrations in the mechanism, but once the reaction is over, it's all gone because it doesn't make it all the way through to the products. So that's what an intermediate is. It's a species produced in an elementary reaction, but it does not appear in the overall reaction. So this hopefully gives you a little bit of a flavor of kind of where we're going with this and how to interpret some of these things that we introduce in this step. Now the second thing we're going to look at is what we call molecularity and how we write rate equations for elementary reactions. Okay, so in the second part of this video, we're going to look at what we call molecularity. And molecularity is basically the number of reactant molecules that come together and react in an elementary reaction. And this is going to be very important for how we write rate equations for elementary reactions. So let's take a look at this and just kind of start to work through what molecularity is and how we write the rate equations, and then we'll apply what we're learning to that mechanism that we had on the previous page. Okay, so the first one we can have is we can have one molecule that comes together. So this would be the number of molecules, and the title for this is unimolecular, or just one. And so an example of this would be something like NO2 breaks down to NO plus O. Now this would be a step. This is not the overall reaction. These are elementary reactions. So keep in mind that these are elementary reactions. So this is not the overall reaction. And if we want to write rate equations for this, we can actually do that accurately. And I'll explain why in just a second. So unlike with an overall reaction, with elementary reactions, we can actually write a rate equation where we put the stoichiometry as the m or the n. And I'll explain why in just a second. So for this, the rate equation would be rate is equal to K times the concentration of NO2 to the 1. And I'm using the stoichiometry here of the 1 as my m. Now, how can I do that? Well, what makes an elementary reaction different from an overall reaction is that in an elementary reaction, we're saying that this reaction takes place exactly as it happens, right? So we're saying that one NO2 breaks down into one NO and one O. And this happens in this precise way, in this precise step. So in this case, we know that this is going to be dependent on the concentration of NO2 in an order of magnitude of 1, meaning the NO2 itself is what's going to control this, because one NO2 needs to break down to make the NO and the O. So we can say specifically that the order here is 1. Now the reason why we can't do this for an overall is because in the overall we don't know what steps are taking place inside. It could be that the rate limiting step, and we're going to look at what a rate limiting step is in the next video, but it could be that the rate limiting step involves one reactant molecule but doesn't involve another. So because we don't know anything about the mechanism for the overall, we cannot write the rate equation based on the stoichiometry. But for the elementary reactions we can, because for those reactions that is specifically what is happening during that step. Okay, so let's look at the second one. So if we have two molecules coming together, this is what we call bimolecular. And an example of this would be Cl plus CHCl3 gives HCl plus CCl3. I think that's actually supposed to be CCl4, so let me correct that. And so for this one, because this is an elementary reaction and we know that one Cl is reacting with one CHCl3, we can say that the rate in this case is going to be dependent upon K times the concentration of Cl to the 1 times the concentration of CHCl3 to the 1. And I'm getting that from the stoichiometry here. But only because this is an elementary reaction. And so we can have a one that involves 3 molecules. This is called termolecular. I actually don't have any examples of this because it's very uncommon. So for example, if we had 2 NO2 goes to N2O4, this would be another example of bimolecular, but in this case, it is involving 2 of the same molecules. So we have 2 NO2s coming together, 2 NO2s are reacting. So another way to think of this is NO2 plus NO2 gives N2O4. So it is a bimolecular because 2 of them are coming together. And what's unique about this one is that the rate is going to equal K times the concentration of NO2. And for this one, we can use the stoichiometry squared because we see that it requires 2 of these NO2s to come together and react with each other. So that's what we're talking about when we talk about molecularity and writing rate equations for elementary reactions. Okay, so now that we know how to write rate equations for elementary steps, what I want you to do is just pause the video and take a look at this mechanism that we had on the previous page. Pause the video and see if you can write the rate equations for these elementary steps. Okay, so for the first one, what you should have gotten was rate is equal to K times the concentration of A squared. And for the second one, you should have gotten rate is equal to the concentration of E times the concentration of B. Now, in the next video, we're going to talk about this in much more detail, how to interpret these things. But a couple of things I want to point out here is, if you look at this second rate equation, the intermediate appears in this rate equation. And that's actually a problem. So one of the things that we're going to work on in the next video is, number one, what do we do if that happens? What do we do if an intermediate appears inside of the rate equation that we think is the one that is controlling the overall reaction? And the other thing we're going to think about is, how can we tell which of these intermediate steps, how can we tell which one of these intermediate steps is actually controlling the overall reaction? Is it one step or is it many steps, and how can we kind of figure that out? So that's the conclusion of this video. This gives you an introduction to mechanisms and how to interpret them. In the next video, we're going to go over how we can come up with a rate law from the mechanism.